Scene script. Have you ever wondered what binds the universe together? What are the rules that govern the stars, the galaxies, and everything we see around us? It's a thought that has captivated human curiosity for centuries, sparking some of the most profound scientific discoveries. One such discovery is the theory of relativity, a groundbreaking concept proposed by none other than Albert Einstein, the physicist synonymous with genius. The theory of relativity is a cornerstone of modern physics and is as monumental as it is intriguing. It is composed of two parts, each as fascinating as the other. The first is special relativity, which introduces us to the mind-bending ideas of time dilation and length contraction. It tells us that the laws of physics are the same for all observers, regardless of their state of uniform motion, and that the speed of light in a vacuum remains constant no matter the speed of the observer or the source of light. The other part is general relativity. This extends the theory to include the effects of gravity, painting it not as a force, but as a curvature in the fabric of space-time itself. It's a theory so powerful that it has given us insights into black holes, gravitational waves, and the expansion of the universe itself. But why should we care about these theories? Are they merely the musings of a brilliant mind, or do they have practical implications in our day-to-day lives? The truth is, the principles of relativity are all around us, guiding the GPS systems that we rely on for navigation, allowing us to understand the behavior of celestial bodies, and even shaping our understanding of the universe's past, present, and future. So buckle up as we take a journey into the fascinating world of relativity and unravel the mysteries of space and time. We're about to embark on an adventure that will take us to the very edges of our understanding, challenging our perceptions of the universe and our place within it. It's going to be a ride you won't want to miss. First, we delve into the realm of special relativity, which talks about the invariance of the speed of light, time dilation, and length contraction. Let's start with the invariance of the speed of light. Special relativity tells us that the speed of light is a constant for everyone, regardless of how fast they're moving or where the light is coming from. Picture two friends, one sitting still and the other zooming by on a rocket. Both would measure the speed of light as the same, even though one is moving fast relative to the other. Next, we have the intriguing concept of time dilation. In the world of special relativity, time is not absolute. It's relative and depends on how fast you're moving. A clock on a speeding spaceship will tick slower compared to a clock on Earth. So if you've always wanted more time, just hop on a spaceship and travel near light speed. Finally, we come to length contraction. This is the idea that objects in motion appear to contract along their direction of motion. Think of a spaceship cruising at near light speed. To a stationary observer, the spaceship would appear shorter than its actual length. But if you're on the spaceship, everything would seem normal. Now, isn't that a mind bender? But wait, you might ask, what about the people on the spaceship? Do they also shrink? Not at all. The contraction only appears to an outside observer. The spaceship crew will feel and measure everything as normal. So, as we see, according to special relativity, the speed of light is a cosmic speed limit. Time can stretch and lengths can shrink. These principles might sound like they're straight out of a science fiction novel, but they're very real and have been experimentally confirmed. They not only revolutionize our understanding of the universe, but also have practical applications in our everyday life. But we'll get to that later. For now, let's prepare to dive into the world of general relativity in our next scene. Scene script. Next, we step into the world of general relativity, where gravity is not a force but a curvature in space-time. Time can slow down in strong gravitational fields, light can redshift, and all observers, irrespective of their motion, obey the same laws of physics. Let's kick things off with gravity, our most familiar force. In the realm of general relativity, gravity isn't a force at all. Instead, it's a result of the curvature of space-time caused by mass and energy. Imagine a rubber sheet stretched taut. Now, place a heavy ball in the middle. The sheet curves around the ball just as space-time curves around mass and energy, affecting the path of anything that comes near. Next up, we have time dilation in gravitational fields. This is where things get really trippy. Remember how we said that time can slow down in strong gravitational fields? This means that clocks in stronger gravitational fields tick more slowly. So, a clock on the surface of the Earth ticks slower than a clock on a satellite in orbit. Now, let's talk about light. Light isn't immune to gravity's influence. When light passes through a strong gravitational field, it shifts to longer wavelengths, a phenomenon known as gravitational redshift. This is why light from a star passing close to a massive object, like a black hole, appears more redshifted when it reaches an observer far away. Lastly, we come to the frame of reference and the equivalence principle. This principle states that the laws of physics are the same for all observers regardless of their motion. So, if you're in free fall, you'll feel weightless. In this frame of reference, the effects of gravity can be indistinguishable from a region of space-time without gravity. Thus, general relativity paints a picture of gravity as something that can bend time, stretch space, and even color light. You might be wondering, how does all this affect me? Well, the theory of relativity has some very real and practical implications. Let's take a look at GPS systems, for instance. These satellite-based navigation systems, which we use almost daily for our commutes or travels, owe their accuracy to the theory of relativity. You see, the satellites that make GPS possible are moving rapidly compared to us on Earth's surface, and they're also in a weaker gravitational field. This means that their onboard atomic clocks tick just a hair faster than clocks on Earth. Without applying a correction based on Einstein's theory, your GPS could be off by several miles. So, in essence, relativity helps us get to our destinations with pinpoint accuracy. But the implications of relativity stretch far beyond our planet. Back in 2015, scientists made a groundbreaking discovery that further confirmed Einstein's theory: gravitational waves. These are ripples in space-time caused by accelerating masses, such as two colliding black holes. Detecting these waves enables us to study cosmic events that would otherwise be invisible. It's like having a brand new way to observe the universe. Speaking of black holes, they're another fascinating consequence of general relativity. These are regions where gravity is so intense that absolutely nothing, not even light, can escape their pull. Observations of stars orbiting seemingly empty space have provided strong evidence for the existence of black holes. Despite their ominous reputation, black holes play a crucial role in the structure and evolution of galaxies, including our own Milky Way. So, whether it's making sure we don't get lost on our way to a new restaurant or helping us unravel the mysteries of the cosmos, Einstein's theory of relativity is continually shaping our understanding of the world and the universe beyond. So, from getting us to our destinations to helping us understand the universe's most mysterious phenomena, relativity plays a vital role. In summary, Einstein's theory of relativity has revolutionized our understanding of the universe. It's as if we've been handed a new pair of glasses, allowing us to see space, time, and gravity in a completely new light. Special relativity, with its constant speed of light, time dilation, and length contraction, has shown us that our universe isn't as straightforward as we once thought. On the other hand, general relativity paints gravity not as a force but as a curvature in space-time, a concept that continues to fascinate us today. From explaining the redshift of light in strong gravitational fields to predicting the existence of black holes and gravitational waves, Einstein's theories have proven instrumental in advancing our knowledge of the cosmos. As we continue to explore the cosmos, the theory of relativity remains our guiding light, helping us unravel the mysteries of this vast, fascinating universe.